Welcome to Ask and Learn.
In this problem, we have a shaft or a rod here, um, extending from a pivot point here. There is a spring that is acting at the top, that's on a roller over here, so it's always acting in the horizontal direction, which would be make some basically minimize the energy. So that would be the minimum distance. If you actually had it pinned at somewhere on the other end, then obviously the length would be a much more complicated function because of the geometry. So it's nice that we just have it, the force is always horizontal, and we have the weight acting, and then we have an applied moment acting. So if we start to write now force vectors at the pivot point, we have this, and I'm going to call that my origin. Up here we have the spring force in the horizontal direction. Its position, and again we're going to call this theta here. So the distance is, the length of this shaft is L, and then the direction is this. And then we have the weight here is minus mg. And then the position is just half of the position here, so it's a uniform bar, so it's halfway up the length. And then we have a point moment acting in the counterclockwise, in the clockwise direction. So counterclockwise would be positive here if this is x and y. So in this problem, actually, all we need to do, because we're not asked anything about these reaction forces here, we can just take moments about this point, and then those will drop out, and then we just need to do a moment balance, and then we get everything we need from that. So if we do that, we just need to, consider the moments from all the forces. F1 obviously drops out of here because R1 is 0. And then make sure we add in the applied moment and set that all to 0. And we only get one equation out of there that's non-trivial. The third component, or the z component. And if we go through it and plug everything in, we wind up finding that this gives us L sine theta times the quantity minus KL cosine theta plus 1/2 mg, and then all plus m4 equals 0. Obviously, I've used the spring constant in here. So we have the spring over here, and then this is F2, right? And then if we say that this is positive theta, then we have that F2 equals K, and then this would be the X component of R2, so we could just say that it's R2 dotted with I, so it best be L cosine theta, and that's where we get, that's where this term comes from, right? So KL cosine theta. Now, solving this isn't trivial, but we can do it numerically or graphically or iteratively or however you want. But in the end, if we plug in the values that we were given, we find that the equilibrium occurs when theta is 24.6 degrees. So given the moment that's applied, the weight here, and the spring constant, and the length, we can figure out what this angle is.